Welcome back to the deep dive. Today, we are undertaking a really essential analysis for anyone working in self-supervised learning, specifically in the video domain.
A very active area right now.
Absolutely. Our source material is the paper Revisiting Feature Prediction for Learning Visual Representations from Video, which introduces V-JEPA.
The Video Joint Embedding Predictive Architecture.
Right. And our mission today is to move past the headlines and really drill down into the architectural choices, the theory behind it, and the empirical results that, frankly, position feature prediction as a superior objective for video modeling.
And the foundational concept here is surprisingly classic. It goes all the way back to Rao and Ballard in 1999.
The predictive feature principle.
Exactly. The idea that representations from, say, adjacent moments in time should be predictive of one another. The novelty here is taking that old principle and integrating it with a modern toolkit.
We're talking vision transformers, masked autoencoding.
And the GPay framework itself, what they've built is just remarkably clean. You need zero external supervision, no pre-trained image weights, no text, no negative examples, and this is critical, no resource-intensive pixel reconstruction.
And the results really do confirm the power of that clean approach.
Yeah.
Let's just cut right to the punchline, because the performance is genuinely striking for a purely self-supervised model.
It is.
They trained a family of these V-JEPA models entirely on unlabeled video, and their largest one, the ViT-H16, it hits 81.9% accuracy on Kinetics 400.
And even more impressively, 72.2% on something V2.
Which is a much more motion-heavy task. But for you, what's the major structural proof point here?
It's the fact that this is all achieved using a frozen backbone.
A frozen backbone.
That's the entire point. It means the features learned during pre-training aren't brittle or just overfit to one kind of task. They are immediately versatile.
So you can just plug and play.
You can plug this representation into an appearance-based task like kinetics or a motion-based one like something V2, and you don't need to fine-tune the base weights. It just works. It shows the V-JEPA objective is learning a really generalizable semantic representation.
Okay, let's unpack the core engine then. The video joint embedding predictive architecture itself. How is the prediction actually framed?
So V-JEPA is built around two key networks. You have the online encoder, let's call it E-theta, and a predictor, P-phi. The task sounds simple, but it's hard to execute.
Right.
You want to predict the encoded representation of a target region, we'll call that Y, given the encoded representation of a context region, X.
Okay, so you see part of the video and predict the features of a missing part.
Exactly. And the predictor is also conditioned on delta E, which is just the spatiotemporal position of that missing A block. It needs to know where it's predicting.
But with any self-supervised setup like this, especially using a regression objective, the threat of representation collapse is, it's immediate.
Oh, absolutely. The model could just learn to output a constant vector and get a low error, a trivial solution.
So the solution here seems to hinge on, what, 3 key modifications to the loss function to prevent that?
Yes. The full training objective is minimize the L1 norm of the difference between the prediction and the target. But the details matter.
Let's break those down.
First, they use the L1 loss, not the more common L2 loss. Empirically, they found it was just far more stable for this kind of task. Second, and this is the fundamental collapse prevention mechanism, you have the stop gradient operation applied to the target representation.
The stop gradient. So it's like an unwritten rule. The target encoder is stable. It can't learn from the predictor's mistakes.
Precisely. The gradient doesn't flow back into the target. And that leads to the third critical component. The target encoder itself, E-theta bar. It's not just a copy.
It's an exponential moving average.
A Polyak average, right, of the primary online encoder. This separation is theoretically motivated, and it's what makes JEPA work. By using the slower-moving EMA target with the L1 loss, the optimal predictor ends up converging to the conditional median of the target distribution.
The median, not the mean. What's the implication of chasing the median?
It means the encoder learns to minimize the median absolute deviation, or MAD. This forces the encoder, E-theta, to capture the maximum amount of semantic information about the context X to reduce the variability of the unknown target Y.
Ah, so if the encoder produces a feature map that's missing key context, the deviation of possible targets is huge.
The MAD increases dramatically, and that provides a very strong, non-trivial learning signal. It ensures the predictor is always chasing a high-quality, stable target.
That makes perfect sense. You're building an information-rich representation, not just a statistically average one. Okay, we have the objective. Let's talk input. How does V-JEPA ingest, 16 frames of video and prep it for a ViT?
Well, a standard ViT needs a sequence of tokens. So to get from raw video to that sequence, they use a 3D convolution layer.
Okay.
And this layer acts as a spatiotemporal patch embedding. So instead of just 2D patches from an image, it collapses these 2 by 16 spatiotemporal blocks into individual tokens.
And the result is a single sequence.
A single 1D sequence of 1568 tokens that represents the entire 16-frame clip. It's a really efficient way to convert that volumetric video data into the structured input the ViT needs.
Now we get to the core of the prediction task, the masking. With video, there's so much redundancy. If you just mask one pixel, it's trivial to predict.
Trivial. Information leakage is a huge problem.
So they needed a new strategy to make the task hard enough to actually drive semantic learning.
Yes, and this is a key novelty in the paper. They introduce a robust multi-block masking strategy to define the target regions. It's not just random masking. They combine 2 distinct types of high-ratio masks.
2 types.
First, you have what they call short-range masks. These are 8 randomly sampled blocks that cover about 15% of each frame. Then you have long-range masks, 2 much larger blocks designed to cover a full 70% of each frame.
Why combine them? What's the intuition?
The combination forces 2 different kinds of generalization. The short-range masks make the model learn local consistency, but the long-range large hole masks, those are what truly challenge the model.
Because it has to infer over a huge missing chunk.
A huge, continuous, and temporally extended chunk of missing information. That's critical for learning things like object persistence or complex actions. With simple random masking, the information leakage from adjacent tokens is just too high.
So what's the final masking ratio?
The average ratio is about 90%, which is very high, far higher than you see in traditional masking techniques for video.
And the ablations in the paper really confirm this. This high-ratio, continuous block masking is essential. It significantly outperforms simpler methods.
It really does. It emphasizes that the difficulty of the prediction task is paramount for getting high-quality features.
Okay, so the encoder is a standard ViT, but what about the predictor?
The predictor is optimized for efficiency. It's a much narrower transformer, only 12 blocks deep, 384 embedding dimension. It's solely responsible for predicting those missing features.
How does it know where to predict?
That's where that delta T term from the objective comes in. The predictor gets the embedded outputs from the context encoder, but it also gets a set of special learnable mask tokens.
And these tokens have the positional information.
They're embedded with the explicit spatiotemporal coordinates. It tells the narrow predictor transformer precisely which location in the feature space it needs to reconstruct. This decouples information encoding from the prediction process, and that's where the massive efficiency gains come from.
Okay, let's pivot to the quantitative results. The paper makes a very compelling case for future prediction being superior to pixel reconstruction.
Yes, methods like video MAE or OmniMAE, they're compute hogs.
So what are the key findings that highlight V-JEPA's advantage?
There are 3 killer arguments here. First, let's just call it loss space superiority. The consistent finding is that predicting in feature space, like V-JEPA does, just gives you better performance than predicting in pixel space.
And why is that?
Because the model gets to ignore all the unpredictable high-frequency pixel noise, it can focus all of its capacity on modeling the semantic, structural components of the video, which is what we actually want in a representation.
So the feature space is just a cleaner, higher-level target. The learning signal is more focused.
Precisely. The second finding is the staggering efficiency gain.
This one is huge.
V-JEPA uses significantly shorter training schedules. For instance, their VITL model processed only 270 million video samples. Compare that to a similar OmniMO-ME model, which required 2.4 billion samples.
That's nearly a tenfold difference.
It's a huge difference in data consumption, and that translates directly to less compute, shorter wall clock time. It just lowers the barrier to entry for training these large video models.
A 10x reduction in samples to get competitive results. That's enormous. It really proves the objective is maximizing the information from every frame.
And the third piece of evidence is all about motion understanding. V-JEPA models show a massive performance gap. We're talking over 21 percentage points on a task like something something V2 compared to powerful static image baselines like Dino V2 or OpenCLipe.
When they're all evaluated with a frozen backbone.
Under the same frozen protocol, yes. That 72.2% score really confirms that the spatiotemporal prediction objective is effectively capturing the temporal dynamics you need for action classification. That's where specialized video self-supervision really shines.
Okay, now we have to discuss a critical piece of the evaluation protocol. The JBAP objective uses an unnormalized L1 loss, so the encoder features aren't guaranteed to be linearly separable.
Right, unlike contrastive models, which means standard linear probing, the normal way we evaluate these things, would actually undersell V-JEPA's feature quality.
So they developed what they call attentive probing.
Exactly. It's a necessary nonlinear feature pooling strategy they use just for the frozen evaluation. Instead of simple average pooling, they introduce a learnable cross-attention layer and a single query token.
And that query token attends over all the features.
It attends over the entire sequence of V-JEPA features, pooling them into one comprehensive representation, which then gets fed into a small MLP for classification.
It sounds a bit more computationally heavy for evaluation, but the results validate it.
The gains are massive. Using attentive probing led to a jump of over 17 points on kinetics, 416 points on something something V2 compared to just average pooling.
So the information is there, it's just not organized in a simple linear way.
Exactly. The latent space is high quality, but the information is structured in a complex, non-linear way. You need a more sophisticated mechanism to extract it for classification.
And beyond architecture, the pre-training data also mattered a lot. The best overall generalization came from their combined VideoMix2M dataset.
Yeah, VideoMix2M, which blends How-To-100M, kinetics, and SSV2, it achieved the best average performance across all the different tasks.
The diversity wins out.
It does. A model trained just on kinetics and SSV2 might get a marginally better kinetics score, but the blended dataset is crucial for generalization. It just proves that even in self-supervised learning, dataset diversity is still paramount.
Finally, let's touch on label efficiency. This is probably the most practical metric for a lot of researchers.
Yeah.
How robust are V-JEPA's features when you don't have a lot of labeled data?
They are demonstrably more robust than the pixel reconstruction baselines. In their low-shot setting, they reduced the labeled examples for kinetics by tenfold.
Okay.
And the largest V-JEPA model's performance only dropped by about 12%. Contrast that with Video MEEV2, which saw its performance plummet by 30%.
Wow, that's a big difference.
It is. It suggests the V-JEPA objective, by focusing on semantics, captures a richer, more abstract, and ultimately more transferable set of features that can generalize really well with minimal downstream supervision.
That gives us a really solid technical grounding on why this method is so compelling. So to synthesize this whole deep dive, V-JEPA confirms that feature prediction is an exceptionally effective and efficient standalone objective.
When implemented correctly, yes. With the JEPA principles in that high ratio masking.
It produces these versatile, abstract representations that outperform prior methods, and it does so while requiring orders of magnitude less data processing.
It's just hard to argue with that level of efficiency, especially when you consider how clean the whole setup is.
And that structural efficiency leads us right into the paper's most provocative final point. There's still a performance gap when you compare V-JEPA on static image tasks to the best image models out there, like Dino V2.
Right, on ImageNet, for instance.
The authors hypothesize this isn't an algorithmic failure. They think it's a data constraint. They suggest the deficit is basically due to the limited visual diversity of the public video datasets they used compared to the internet-scale image data used for Dino V2.
Which shifts the problem entirely. It's not about the algorithm anymore. It's about the infrastructure.
Exactly. And that raises a crucial question for you, the listener, who's operating at the cutting edge of this field. If the algorithm is now this efficient, what are the combined engineering, infrastructure, and frankly, legal challenges in constructing a diverse, truly internet-scale public video data set that's needed to close this final performance gap? It seems that data scaling, not necessarily model architecture, might be the definitive final frontier in unsupervised video representation learning.